Welcome to APEC. It's September 17th, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, we are honored to have Dr. James Woodward with us to discuss Mach's principle and his team's Mach Effect Thruster experiments. Franc Milburn is going to be providing details on UAPs and the DoD's All-Domain Anomaly Resolution Office, and Gary Stephenson will be presenting on superluminal quantum communication. We'll be finishing off the event with open discussion and ad hoc presentations by conference attendees. So a couple of quick reminders. You can view conference replays, details, and speaker info on our website at altpropulsion.com. Please save your questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type those questions in the chat. We will try and go through them after each presenter finishes. So let me, without any further ado, introduce you to our first guest. Again, it is a true honor to have Dr. James Woodward with us to discuss the Mach effect. Now, this postulates that energy storing ions experience transient mass fluctuations when accelerated. Unlike conventional technologies, drives based on the Mach effect don't need to release matter in order to generate thrust. So let me introduce James to everyone, and I'm going to hand things over to him to get started.
When Tim invited me to do this several weeks ago, and I said yes, I thought about doing a short presentation. Then I figured, well, there's some other people in the project who deserve to have a little visibility, and I asked Paul March and Michelle, and actually a few others, if they'd be interested in doing parts of this show. And Michelle and Paul both said yes. So Michelle, are you planning on showing Paul's slides when we get to the Paul part of the talk? Or are you, well, when we get to the Paul part of the talk, we'll see, we'll find out. This is a title slide which I put together last night.
Yes.
A number of years ago, had the clever idea of putting together Mach effect, which had been typically used as Mach effect thrusters, as Mach effect gravity assist thrusters. But it dawned on me that these things are not really gravity assist thrusters in that sense. They are actually impulse engines of the Star Trek variety. That is to say, engines that you can use to accelerate something to sublight velocities, but not faster than light. You need warp drives or wormholes to do that. And I added the bottom part, first step on the pathway to the stars, because the physics that underlies Mach effects also has something to say about the nature of gravity and inertia that's important for figuring out how to do the wormholes and warp drives. Next slide, please, Michelle. Michelle. Aha, here we go. Okay, lots of people have been involved in this project over the years, and I've listed a few of them. Gary Hudson at the Space Studies Institute has been on board with this since around 2005 or thereabouts. We have received unstinting support from SSI, and I want to say how much we appreciate that. The current 4 participants are Michelle Royals, who's switching slides, David Jenkins up in Sacramento area, and Paul March in Friendwood, Texas. We have a couple of recent arrivals, actually several. Curtis Horn, who was a grad student of Hal's back in the early teens, and Christopher Obafunwa, who has created a corporation which he hopes to use to exploit this technology, and along with others. It's called, oh damn, I'm blocking that. That's one of the problems with getting old. You block on things that you know very well. No. You'll notice when you see the name of this corporation, you'll know what he's up to. Okay, next slide, please. Okay. When I put together this talk, I used the most recent PowerPoint talk that I had used before and started doing modifications, and it's got some movies in it. I couldn't come to get rid of the movies. So Michelle, you get to go to the next slide briefly. Oh, movie, that's it. Okay. Okay, next slide. Star Trek, science fiction. Yeah, you can skip the next two slides too. One of them, these are short clips from George Powell production of War of the Worlds. Okay, the third one, which is a movie, can you play the movie? No, back one. Can you play that movie, Michelle? It won't play, huh? That's a shame. Well, I can tell you what it is. It's from the opening of a movie called Forbidden Planet that came out around 1958 or thereabouts. And in the opening, they got the timing of various space achievements seriously wrong. And then went on to say around 2400 or thereabouts, people figured out how to make hyperdrives and achieve the speed of light and vastly exceed it, so on. I remember seeing it as an adolescent. You know, I was probably about 14, 15 at the time, and thought to myself, well, hell, if they could figure out how to do it 2400, why not figure out how to do it now? It's a matter of commitment to a project, not a matter of, you know, time elapsing. I, of course, being still very young, did not appreciate how slowly advances in scientific knowledge can proceed. Okay, next slide, Michelle, please. The other thing that happened in the 1960s was I observed a satellite with friends while indulging myself in flamenco guitar in Spain. I saw a satellite change the plane of its orbit by more than 90 degrees. And I knew that was physically impossible, at least for us. So it convinced me that somebody had figured out how to do something that we didn't know how to do, and that I would spend some time working on trying to figure out how to do it. Okay, next slide, please. Okay. The other thing that turned out to be really important was I had an instructor, as a matter of fact, one who I take a graduate course at NYU in physics with, and I went to him with a problem I was having with general relativity and all that. And I allowed us how I was having a lot of trouble with it. He laughed at me. He said, everybody has trouble with that. Don't worry about it. Then he said, look, if you want to become the world's expert on something, what you need to do is you need to take up a very hard problem. The reason why you want to take up a very hard problem, if you're willing to spend years, if need be, on it to solve it, okay, is because if you pick the problem that isn't that hard, lots of very smart people will probably beat you to the solution. On the other hand, if you pick a really hard problem, they won't bother to do it till somebody shows that it's tractable and usable. Okay? So yours truly picked a really hard problem and have worked on it ever since. And maybe we're getting somewhere. The other things on this slide, Mach's principle and the origin of inertia. What I want to say about this is that this was put together when I did not understand what Einstein had done about the nature of inertia. I sort of generally knew, but had not worked out the details of it. Mach's principle was named by Einstein in 1918, and he proposed that the distribution of matter in the cosmos was the reason why objects have inertia. It's not something that's conferred on them simply by being existing in empty space. As a matter of fact, he didn't think there was any empty space. He was convinced that the only solutions of general relativity that made sense were ones where space-time is a gravitational field. And he was also convinced that space-time being the origin of the gravitational field of cosmic matter must be responsible for the inertia that we see. The reason why this is important, and I mention it now, is because Mach effects and propulsion, the reason why I call them Mach effects is because you have to understand inertia as a gravitational effect. Okay, if you say Mach's principle is wrong, that their inertia doesn't have anything to do with gravity and all that, you can't do what I'm going to be talking about. You may want to write it down on paper and say, no, it's the reason why it isn't the origin of inertia. Okay. If inertia is gravitational, then you can figure out how to make impulse engines. That's the last point on this slide. Next slide, please, Michelle. Yeah, okay. This is a title slide for the talk for phase 1 grant that Al did. And then the next one is the title slide for the NIAC, NASA Innovative Advanced Concepts program. They gave us some money a few years ago and we tried to spend it sensibly. The people who were involved in phase 2 are listed there. Okay. All right, next slide. Tom Rosa, by the way, did really nice artwork for that one. This slide I attached for the Hal. It has to do with the business about gravity and inertia and all that. This is Hal's way of saying what needs to be taken into account in general relativity. The reason why space-time, according to general relativity, is flat when there are no nearby local masses is because the distant matter in the universe acts like the springs in the trampoline that you see on the left to stretch the space-time flat. Okay, and when you put something down on the space-time, it distorts the space-time. The space-time distortion, of course, is impossible if you don't have space-time there to start out with. If you have an empty universe, there's nothing to distort. Okay, next slide, please. This, by the way, says that you can read this slide for yourself. Okay. What it says is cosmic spatial flatness is a special condition in general relativistic cosmology. It's the so-called K=0 solution of FLRW cosmologies. And it has a very distinctive characteristic. It's an energy condition determines whether space-time is flat or curved. The energy condition for flat space-time is that the locally measured Newtonian potential due to the matter density that's uniformly distributed throughout cosmic space-time, that potential is exactly equal to the square of the speed of light. Okay. This turns out to be useful because, next slide. Okay. Yeah, that's all I just said. Okay. It turns out that they are locally measured invariants, so they always have the same number when you measure them locally. but they are not global invariants. So the deviation from what you measure locally, even quite nearby, may be non-negligible. And indeed, that's the case in, say, the Earth's gravitational field. The reason why you're being accelerated towards the floor at 9.8 meters per second squared is because the difference between the local potential where you are sitting and 5 or 10 feet away from you is sufficient to produce a small change in the acceleration and so on. Okay. So what we're going to do now is something that I did back in the fall of 1989 and 1990 and 91. Consider the Newtonian approximation to general relativity is written by George Luchak in the early 50s. Next slide. Okay, those are the gravitational field equations he found. Luchak was interested in pursuing something else coupling to the electromagnetic field because Patrick Blackett had suggested that there might be something there. When he wrote down the field equations which he coupled, he didn't need general relativity, so he just wrote Newtonian gravity, but he took the trouble to write it out in a relativistically invariant form. What that means is you get time derivatives in your equations, because the thing that relativity does by having a maximum velocity is it means that the speed of light is finite and that time delays take place for propagation effects and so on. Okay, so his field equations just F up there by itself without the time-dependent terms looks like Newtonian gravity, which it's intended to be. But relativistic invariance introduces those 1 over c dq dt terms or 1 over c df dt. The 1 over c dq dt term is the one that's really important. Okay, I think next slide. Let's see if I'm at the next slide transition yet. Michelle? Okay. Go back one slide. Okay, equation 3 allows you to write the field F as a gradient of a scalar potential. The field's irrotational or conservative. Since Q, the rate at which a gravitational field does work on its local sources, is just the partial with respect to proper time of the proper energy density, where the proper energy density is the proper energy density is the matter density times c squared. Gravitational induction of inertia allows us to write 5 for c squared in that equation. And if you carry out the necessary algebra in equation 1, the QDT turns out to be the second derivative with respect to proper time of the proper energy density. Okay, and that's a straightforward calculation. Instead of just having Q, you now have rho c squared as the thing that's being acted upon. Well, you take the time derivative and all that. And what you get is the next slide. Okay, Michelle, next slide, please. Okay, the left-hand side of this equation, basically what you're doing is you're separating variables and looking for a term which is 1 over c squared b squared phi dt squared, okay, because that completes the D'Alembert, so-called. The left-hand side of this equation is a classical wave equation. Okay? It's equal to the sources. Now, if you didn't have any of those other time-dependent terms on the right-hand side, it would be just minus 4 pi g rho, okay, which would be Newtonian. But the time derivative of this proper energy density, the second time derivative, the proper energy density leaves, in addition to the term on the left-hand side of the equation here, a bunch of time-dependent terms that are shown on the right-hand side of the equation. Okay. They are transient. The reason why I got interested in this is because I was not being very successful at something else. I looked at it, I thought, well, hell, that may be large because you may be talking about a very small energy density. But if you could make a change very quickly, you can produce very large effects. And that, in fact, is the case. The first of the time-dependent terms, the one with the coefficient phi over rho c to the fourth times the second time derivative, so on, that could be made fairly large enough, in fact, so that it should be visible in the laboratory. Okay. If you're going to write those transient terms as normal mass terms, you even get a boost out of that because they started out on this field side of the equation. They don't carry the coefficient 4 pi g. And so if you want to write them as normal massive sources, you have to multiply them by 1 over 4 pi g. So that when 4 pi g is the coefficient of rho in this equation, it's multiplied times the, you get back the field with the source terms without 4 pi g in them. Okay. That gives you back the next equation, which is on the next slide. There it is. That's the Mach effect equation. It's obtained simply by using the relativistic Newtonian approximation, doing some fairly elementary algebra and all of that. And what you end up with is this equation. The term of interest to us today is the one in green, and which I just said for you. Notice the 1 over 4 pi g multiplies both all of these terms. The second term is interesting because it has the square of the coefficient of the first term. Okay, times the first derivative with respect to proper time of the local energy density squared. Okay. The thing to note about this is that it's negative definite. Okay. It doesn't matter whether the energy density is positive or negative, as it does in the case of the first term, because it's going to get squared. Okay, so it's going to be positive no matter what the sign of the zero is. And the same is true for the coefficient. All that, and all of that gets multiplied by a minus sign. This means, what this means, of course, is that there may be a way to generate significant amounts of negative rest mass, so-called exotic matter, using the first term to induce circumstances where that takes place. But we're not going to worry about that today. That's UAP stuff. And so we're going to go on to the next slide and talk about how do you actually do this. The answer is obvious to anybody who's fooling around the lab stuff. You can change the local rest mass, proper rest mass of a capacitor simply by charging it up, discharging it. Okay. So, and this can be done electrically very, very quickly. So you got a very large rate of change of time. That means that the E equals MC squared. M is now fluctuating because the capacitor is being charged and discharged. Okay. The fact that that's taking place is fine, but to get it something useful out of it, what you have to do is you apply a force to it. When you apply a force to it, you excite the gravitational force of all of the distant matter of the universe. because inertia, which is what you feel when you push on it, is gravitationally induced. Okay? So what this means is that you can exchange energy and ultimately momentum with the universe using piezoelectrical electromechanical materials. You don't need the electromechanical materials to induce the Mach effect. All you have to do is change the energy of the capacitor and you will get a Mach effect. But to make it useful, you need to accelerate something in which that change is taking place. Next slide, please. Okay. Gravity assist engines. Next slide. The basic idea is very simple. There are three elements in this. The first element on the left, reading left to right, is called Rm for reaction mass. If you have a fluctuating actuator, in order to make it accelerate something else, you have to have something that it pushes against. In the case, for example, of shooting your AR-15 or whatever, it's the impulse that you feel on your shoulder or your side or whatever when the bullet fires. It's pushing back against you. You need an anchor, if you will, push or pull. A is just the actuator. This is just a stack of PZT crystals. And the Fm is a fluctuating mass. Early versions of all this, all three elements were discrete. Went along about 1999, thereabouts. It dawned on me that you were wasting your time with separate actuators and fluctuating masses, that you could just use the actuator, PZT stack, as a fluctuating mass. So next slide. PZT stacks are relatively easy to build. They're PZT disks. They are polarized. You set them up with their polarizations this way, and you glue them together with brass electrodes in them. Okay, next slide. What you end up with is something like this. You always want to include an accelerometer or a strain gauge in these devices so you can see mechanically what's going on. Next slide. Okay. This is a picture of a couple of the remaining devices made this way. And the reason why the pictures are up there, you can see it's relatively simple. Basic parts of an aluminum cap that is bolted down and preload the PZT stack underneath it on the brass reaction mass so that it doesn't tear itself apart. And the thing to note in this picture very quickly is that between the brass reaction mass and the aluminum bracket, which is attached to the rear of the brass reaction mass, you see little black ears sticking out. They're almost completely cut off. Michelle, could you get the cursor on the rubber pad between the brass reaction mass and the mounting hardware? Closer, no, the other way. That's it, there they are. Yes, that's one of them, that's another one, that's another one. Okay. When I first built these things, I did not have the rubber pads in there and they didn't work with beads. Okay. Putting in the rubber pads, all of a sudden they work. And for years, that's what we use, rubber pads. Next slide. The way you measure very small forces, because forces expected were on the basis of micronewtons. No more preferably, but micronewtons was what we built the balance for. Tom DeHood, who had been a graduate student with me in the late 1990s, stuck around with the project long enough to help make this balance, which is the next generation after the so-called Austrian Research Center's balances. It was model of their balance in general terms. It's a balance which is still in operation, and it looks pretty much the same. As a matter of fact, I'll just take one. And there it is. I'll put up down in the back. Okay, let me go through it real quickly. There are counterpoise masses on the left-hand side. The gallant stand contacts are mounted in the central column, which is where the C-flex bearings, which allow this thing to oscillate horizontally, are located. And then to the right of that, there's wiring. The shielded wiring goes into the beam and down through the end of the beam and so on. The calibration technique is a 3-coil setup wound on 35mm film caps, canister caps, 10 turns each, works very nicely. And we even had George Hathaway check up on us and make sure that that was working as we played. On the right, you see Faraday cage. That's the aluminum box, which is held on pieces of red plastic that form a vibration isolation yoke. Okay, next slide. That's a C-flex bearing. You can see the cross metal parts. It works beautifully. They're great gizmos. Next slide. That's the yoke, end view of the yoke from some time back. But you can see there are a whole bunch of little brass screws in there. The brass screws compress rubber O-rings. There are rubber O-rings as well as brass screws and washers to kill the high frequency vibration. Next slide. That's a current version of the vacuum chamber, which I just showed you with the webcam. That's probably easier to see. The black column that Michelle has a cursor on right now is monopod in Curtis's terminology, supporting a Logitech Brio webcam with which we take movies of what's going on inside the vacuum chamber. Okay, next slide, please. This is Paul March's, how should I put it? Simple. Simple block diagram of the parts of the apparatus and so on. Okay. Basically, what it boils down to is you measure several things when you run this. You measure the position of the Philtech sensor, okay, which tells you how much the beam has been deflected from its zero position. And you measure the temperature of the device with the thermistor, which is embedded in the cap, the aluminum cap of the device. You measure the strain gauge signal, which tells you mechanically what's going on in the stack. It's a passive instrument. Okay, let me note one very, very important part of this setup. It's the transformer. The transformer turns out to be a critical element in this setup because it's the thing that enables the Steiner Martin's 111 piezoelectric materials that we use to generate copious higher harmonics. And you need more than one harmonic to make these things work. You need at a bare minimum a first and second harmonic. The second harmonic is a force rectification signal. It's something that pushes on the thing when it's more massive and pulls it back when it's less massive. Again, push when it's more massive, and so on. The mass fluctuation takes place at twice the frequency of the base signal. So the second harmonic is absolutely essential. And you don't see much second harmonic in these things unless you have the transformer in this setup. Next slide, please. Engineering larger thrusts, okay, for the placement for the rubber pads. Right. Next slide. Okay, yes. The first attempt at this was to put washers instead of rubber pads between the aluminum bracket and the reaction mass. This is a picture of one of those devices with the washers. It actually works, believe it or not. It significantly improves the thrust over the rubber pad. The problem is they die very quickly. So we were poking around for another way of doing this. Next slide, please. But before we turn to that, Paul was going to give a talk. Paul, I hope all is well at home, Paul. Okay. We're going, Paul's slides will be available, I assume, through APEC. The way in which we resolved the problem of the washers dying was to note that in addition to the washers, we had also put sledges on the device. This was basically a little mechanical mechanism that allowed the aluminum bracket on which the device was bolted to slide back and forth and free up this sliding. And eventually it dawned on us that probably we didn't need the aluminum bracket at all, that we could do this simply by having a device with ears on it, ears on the reaction mass. Next slide. It looks like this. Okay. This is actually a functional device, current design. The ears you will see are constructed not with Teflon tubing or something like that. When we were trying to figure out how to do this sensibly, we were having an argument, well, what about the coefficient of friction of this and that, the other thing? And finally, Jose Rodal said, gee, what we need is miniature linear bearings. He said, but they're probably prohibitively expensive. And within minutes, Paul and Chip Aiken had both found linear ball bearings, and they were not prohibitively expensive. So the current design for, how should I put it, journeyman work with these things has linear ball bearings into 3 years. As you can see in this rendition, you can see the PZT stack above the reaction mass and the aluminum cap that preloads it. And you can even see the thermistor leads coming out there in the center of the aluminum cap and so on. The accelerometer is the red-green wiring, and the blue and yellow is the power lead to the device. Next slide, please. That's a linear ball bushing. You can even see some of the bearing races in the opening. It's about 4 millimeters in diameter, 2 millimeter throat, and 5 millimeters length. A little bit more than the ears in which I go, so that the ball bushing can center springs that you have to put in. Next slide, please. There's one of these new versions constructed. You can see the very light springs that center it on the rods, and you can see the linear ball bushings just peeking out of the ear in the foreground and so on. The red plastic tab is part of the thing that you suspend this with in order to work. Okay, next slide. The chief criticism of the Mach effect work, as you will discover if you go looking for it, has been Mark Tamar and his students who claim that nothing but vibration is going on. It turns out that there's an easy way to discriminate vibration from real effects, real forces. Vibration is a result of putting energy into the system without communicating any momentum. And if you put energy into one of these devices, you will make it vibrate very strongly, as a matter of fact. And of course, if it's attached directly to your torsion balance, it will make it vibrate too. You will discover if you read Barclay's paper that's what they did as soon as Hal left after depositing a device of the earlier design with them. As soon as Hal left, they took it out of the vibration isolation group, bolted it right to their balance. Okay, it got a lot of vibration. Momentum conservation, however, dictates that when you create the vibration, if a stick-slip mechanism makes the thing move in one direction, it must also make a comparable amount of momentum move necessarily in the opposite direction. There's a momentum 0 to start out with, so it has to stay that way. The significance of that wasn't really fully appreciated until Hal insisted that we do work on a pendulum. We built a pendulum and we did the work on it, and it was wonderful from this point of view, because you could tell easily just by measuring the position of the device and the pendulum support structure and tell whether or not they're moving in the same direction. If they're moving in opposite directions, you're looking at vibration. Conservation of momentum dictates it. If you see the motion of the two parts, the support structure and pendulum, or the support structure and torsion balance, and the device itself, if they move in the same direction, that is only physically possible if a force is applied to the device, which then entrains the pendulum or the torsion balance and forces it to move with it. Okay. This turns out to be critically important because you can measure both positions. Okay. I'm not going to show you pendulum results because that was one of the things we learned was not carefully enough considered. When we ran the pendulum, we assumed that the device did not produce an effect in air. And there were some pretty good arguments for it and all that. But eventually, George Hathaway and Vidal Baltrini both got on me about, oh, you've got to worry about air currents. And so finally last spring, I worried about air currents. And they were right. Air currents, these things act as little air pumps. So you have to do something either to contain and eliminate the effect of the air currents, or you have to put something in a vacuum chamber and get rid of the air currents by removing the air. We've resuscitated the balance, which after the pendulum had fallen into disuse, and it's still in the process of being brought back up to optimal status, but it's working well enough now so that you can actually do experiments. And if you know some other stuff, you know what you're doing. Okay, next slide, please. Torsion balance. The reason why you don't want to use a torsion balance to do this work, why pendula are so much more interesting, is the torsion balance introduces a large moment of inertia, which is a problem. Because if you have a device on the end of one of your torsion balance arms and it's producing a force in a particular direction, and it has to drag an enormous amount of stuff along with it. Okay? Because it's pushing against the springs, which are pushing against the pendulum, and so on. That's one problem. But the other problem is that if there is a vibrational effect present, the motion of the torsion balance beam in the direction opposite to the direction of the motion of the device is much smaller than the motion of the device. And it's easy to miss if you're not paying attention. And next slide, please. Working through all of these things, then you need some luck. Okay. August 12th, run 7 is, in my view, the Great Spirit's way of kicking you in the pants and saying, hey, you're being unnecessarily cautious, dummy. Okay, because August 12th, run 7 happened by accident to get everything exactly right. Okay, next slide is the movie of this run, which you can't see. Michelle, am I correct that you can't show the movie of run 12? Run 7? Next slide. Yes, next slide. I was going to explain to you all of the display things and all that, and let you watch run 7 on August 12th take place. This is the picoscope strip chart recording of run 7 on August 12th. And the red trace is the location of the device as measured by the Filtech position sensor on the opposite end of the beam. Okay, the scale for those red traces is that full scale for the red trace is about 500 micrometers. And so you're looking at a trace of something that's on the order of 300 to 500 micrometers. And you come in on the trace, there's a little blitz there, and then you hit the principal resonance. The thing vibrates a bit, then it goes south, north, then south, down briefly, and then it comes back up, vibrates more, then it stops. Okay, and you get 4 repetitions of that with small changes due to the fact that, as the green trace shows you, the device is heating up during the run. Okay. Are you going to be able to show movies, Michelle, when you're part of this? No, probably not. Oh, God. All right. Okay, let me see. Let's see what I can do here. That's what I can do. I put these are tracking software. All right. While all of this was taking place, Michelle was worried that yours truly, and maybe some others, but mainly yours truly was unduly optimistic about producing real Mach effects. And so when this trace came along, she decided that what we had done here was not good enough. And just getting that red trace with clear behavior of the presence of a real force, which with a variety of tests you know is not due to a bunch of things that you might guess. She was concerned that it might not be a real Mach effect. In the weeks before that, she had found a software program called Tracker out of MIT, is it, Michelle? I think. Anyway, she found this Tracker software, and if you could see a picture of the device, you notice that there are tracking marks added to it for this purpose. So she ran Tracker software on this run, and to her surprise, it turned out that those red trace responses, those are real. They are not just vibration. And there are real forces involved in what's producing that. And we are now at the point of trying to get this everything together so that we could do a set of fairly straightforward tests that show that what you're looking at there is not a mistake or an accident, that it's a real effect. that Einstein was right about inertia being gravitational. And since he was right about that, it means that those weird additional terms that show up is the relativistic Newtonian approximation. They may not be exactly right. A full relativistic version of this in strong field circumstances has not yet been calculated, but if so, that's the first step on the pathway to the stars. Next slide, please. Michelle, tracker, and beyond linear bounds. Michelle, you get to take over. Michelle? This is your cue, Michelle.
I'm sorry, Michelle was muted. Michelle, I just asked you to unmute, and then here, let me do this. Okay, I'm going to remove the spotlight from Jim, and I will put the spotlight on Michelle. There we go. Ma'am, you are all set.
Okay, thank you, Jim. And thank you, Tim, for hosting this. I got to get out of this here. And bonk. And I'm going to do some sharing. And do a slideshow. This is going to be very simple. There's going to be no math involved. It's going to show data and builds and results. And I wanted to thank everybody else that was on this team: Gary Hudson of SSI, Jim Woodward, Hal Fern, Paul March, David Jenkins, Christopher, Uba Funwa. I'm sorry, Christopher, I got your name wrong. Curtis Horn and David Mathis. And Tim, thank you for hosting. This is the tracker software that Jim was talking about. And I'm not sure if everybody recognizes this picture up in the top left corner. But what the tracker software does is it allows me to pick points. And what we have done is, if you take a look at the bottom right corner, this is the Fullerton's torsion arm assembly, and you're looking at the end. You're looking at the working end down here. This is the device that's sitting inside here. Here's a little brass reaction mass. There's a little PZT stack, and there's the aluminum mass at the end. You can see that that is attached to that red plastic bracket that sits there. It's screwed in, and that's attached around to a U channel, which is vibration isolation and dampening, and which goes back to the back of the stack, or the back of the torsion arm, which has the Philtech sensor that's able to detect movement back and forth. So what we did here, and I'm not being an optimist, I'm being a critic here, and Jim says that, is I said, okay, if this aluminum bracket here, which is essentially attached to the torsion arm, if I target that with this tracker software that was made available by open source physics to teach students motion and conservation of momentum and stuff, if I can use this piece of software to track these two devices, I can get an idea of what is really happening, what is the device doing, how its movement's tracking, and what's going on with the torsion arm. So I did. So what this particular slide shows here is that this is that number 7 run. It has been matched time-wise to the tracker software, which at 30 frames per second I analyze each independent frame, each target, and its movement. And as you can see on this particular red one, which is over here on the large aluminum mass, the large aluminum bracket that's attached to the torsion arm, you can actually see how it mirrors the Philtech torsion arm data. As you can see, it goes up, it goes down, wiggles around a lot. You can see a lot more in detail, action and reaction, Newtonian operations here, where the torsion arm kind of dampens it out a little bit. The green trace down here at the bottom, that's the actual device. This is the device that's actually, excuse me, operating back and forth and wiggling back and forth on over time. And this is about I think it's a 25-second run. And you can see it as it bumps up and down and runs around as it gains mass and loses mass, and changes energy and swaps it with this. You say, well, these look pretty identical, but this is where just looking at a simple picture can say that's not exactly what's happening. So if we take the device, which is on the top here, and then take the torsion arm, which is on the bottom here, and we compare them, some things become very, very obvious in this. Number one, when the device is operating under normal Newtonian mechanics and conservation laws, you'll see the device, the device go one direction up here, and then the torsion arm go the opposite direction. I expect that. You should expect that. That's Newtonian mechanics and operation and the conservation laws. But what becomes very apparent here is when the device during this frequency sweep hits resonance, it accelerates and compresses into the springs and pushes the masses, and then it starts showing up in the device. The device, because we're compressing springs and we're moving 160 grams of mass here, is trying to move like 700 grams of mass, or 800 grams of mass. There's a small delay. So the device pushes in and holds through a frequency sweep. The device slowly follows. And the device is delayed about just under a second here. So what you, or not the device, but the torsion arm. So what you see here is a slight delay of the torsion arm's response to the device. You see acceleration, you see acceleration. When it gets out of resonance, which is shown by this here, normal Newtonian mechanics take an effect again. You'll get an opposite reaction back and forth. This is what it kind of surprised me. I didn't expect it to show up like this. I didn't expect to see this delay, but there is. And it agrees with the calculations of the spring compression, the dampening mechanisms we have on the torsion arm. That number comes out just about right. So let's take it one step farther. Let's look at everything that is moving at the end of the torsion arm. We're going to take a look at all the items here. We're going to take a look at the end of the aluminum end cap. I targeted a screw. I targeted the end of the PZT stack. I targeted the brass reaction mass. I targeted the aluminum bracket, and I also targeted screws back here that attach to the torsion arm. So everything moves in this. And if I take all of these and track them all at the same time, I end up tracking everything that moves on the torsion arm and the device. And I end up with a lot of interesting data here. The two centers here are pretty much identical because one is the aluminum mass, which is the red, and the other purple one is the screw. So they're going to be pretty identical. They will not agree with the green over here, which is the brass reaction mass, green dot right over here that you can see, or the other end of the screw that I was tracking up here, which is this one here. Those two agree, these two agree, and this one here is the middle of the brass, or I mean the PCT stack. So if I take all of those and say, where's my center of mass? And I use the center of mass is the key to this entire Mach effect. I use all of these, calculate it out, and say this is my center of mass. This is actual acceleration data of the entire torsion arm being driven by the Mach effect device. And as you can see, as I go sweeping through the frequencies, it pushes the entire torsion arm and holds for at least 2 seconds. In some cases, a little bit longer. And the interesting thing is as this particular run, the device started off really slow. It heated up a little bit, and it got a little bit more relaxed, and we started getting more acceleration data being shown, so that it shows that we have a very nice thrust impulse. I'll take all of these and put them together in a graph, track them all at the same time, and display it. And I'll explain to here what I see in this display. And it's kind of interesting if you take a look at what's happening with the torsion arm and the device and the Mach effects. Number one, the turn-on points, which are in these boxes here, shift a little bit as the device heats up. It shifts about, oh, I don't know, 75 hertz from the center of resonant frequency. That was interesting. That agrees with the calculations. What also is interesting is when the device goes into resonance and it's sitting on these bearings, and the bearings are sitting on these stainless steel rods, they actually float. The vibrations cause the bearings to pretty much float. They bounce around and they float. They use the vibration technique in MEMS to unlock MEMS devices that rock back and forth. So what happens then is the device goes into resonance. It accelerates down. The torsion arm shows that acceleration as just a little bit of scruff up here in the red display. The center of mass saying I'm heading down, and this moves down. And here's our delay on our torsion arm. As the springs compress and it pushes the entire torsion arm in one direction. This is taking all the movement data from a torsion arm and a device hanging on the end, calculating out the center of mass to pull out the Mach effects from non-Newtonian operations, which is exactly what happens. So what this has shown us is the comparison, the data point comparison with the tracker software targeting the points, the different points on the torsion arm with the picoscope data, which is off the Philtech sensor at the other end, shows in exquisite detail a frame by frame motion processing of over 1,800 frames, and it highlights and shows the device's Newtonian conservation actions, and it also shows the Mach effect actions and brings them out to the forefront. And thank you. I have, I'm going to stop sharing screen. I have another presentation that I need to do.
Wonderful. And yeah, and Michelle, you're still spotlighted. So let me know if I can assist at all, or if you're all set.
Oh, I am. Hang on here. I'm trying to get. Here we go. All right, does that screen come up? Do I have a new screen up?
Yeah. Let me see. Yeah, well, I had a slideshow. It looked like it was the other one though.
This is number 2.
There we go. Mega driven past and future.
Yes. I just want to give a real quick review of when I joined this team about 2 years ago. And a lot has happened in the last 2 years to kind of refine the data sets that we're getting out of the devices. This was shown by Jim's presentation earlier, and this is essentially, I don't know, it looks like a Borg torsion arm. And it works very well. And if you know how to interpret the data, you can get some good results. And this is their vacuum chamber, which Jim showed. And they presented some results in a paper, I think it was for a proposal for NIAC, which they had thrusts for about 5 seconds or so. But it was like under 10 micronodes, nothing to write home about. This is their little bracket they had with the little composite fiber washers. And when I joined in the Zoom meetings, we went through a wonderful discussion of how we could enhance the device and how it was sitting on the torsion arm. What are the things that we could do to amplify what the device was doing? So we did. Number one, we said, okay, since we have a clear vacuum chamber, we're going to hook up a camera to it. And this is Hal's first attempt at hooking up a camera. She actually grabbed Jim's magnifying glasses so she could focus in on the device, and you know, it worked. Sometimes in science, you do what you can to make things work. So what we found out was kind of unexpected. We had the device on the bracket. We didn't see much of anything. But when we turned around and we took the device and supported it with those linear bearings that run through the center of the device, and we coupled springs, and those are actually, I think they're like 11 mil guitar springs. And of course, Jim had to have gold-plated ones. And we attached those down into the center of the mass of the device. We did frequency sweeps across the device, and lo and behold, the device says, I am going to move. I need to move. I am shifting and changing my mass. so we had, and it allowed us to turn around and, do some very rude measurements by setting up a scale in the back and measuring the movement of the device, which we found out is about 0.5 millimeter, which was surprising. In the meantime, we started optimizing. We found some springs that worked very, very well. We had the linear bearings. We mounted those all up into the device, which is down here in the bottom left corner. And we turned around and stuck the device into the vacuum chamber. At the same time, we took a laser vibrometer, which can measure high frequency vibrations and movement, because we knew the device was wiggling around in there, and we wanted to see exactly what was going on. Well, we found out that the device does oscillate. It does move. It does breathe. And the device only really breathes about 5 microns in and out. But it does it at about 35 kilohertz, which is the resonant frequencies. And that 35 kilohertz, as it's breathing in and out, is the shifting and the creation of the Mach effect. So while all that was going on up here in the Rockies, Colorado Rockies, I started setting up my lab. I went, well, there's a lot of problems going with a torsion arm. So instead of a torsion arm, I think we're going to do a set of linear air bearings. And these are port air bearings from a company called New Way. They consume very, very little air. It's something like a cubic meter over an hour. But they're very stable and they're friction-free. They're frictionless devices. So got an optical table from Thor Labs, picked up all the hardware I needed from New Way, decided to set a carbon fiber plate up and attach it down to the arms, which we eventually ended up with taking the air bearings and putting them to the outside so we could take a little bit of extra mass off. But we also turned around and, excuse me, we also turned around and gained some mass because we were moving the rods back and forth, the stainless steel rods back and forth. Then we turned around and we said, we're going to mount everything on that we have to onto this carbon fiber table so we can float it. And we did. We ended up with about a mass of about 7 kilograms, which is a lot. But at this particular time, we were running the devices in air and we were seeing false positives as far as thrust, millinewton or higher ranges. And we could have moved this mass. And I could have monitored this mass with Filtech sensors. But also in the meantime, this is it all completed, running on air. This is also testing Jim's device, sitting on the linear ball bearings in this little plastic bracket. It looks like a tank from Tron, I think. So, and I got some results off of it, but like I said, the results have been proved kind of inconclusive because the device can move air. At the same time, I turned around and said, there are some issues, always issues with going with mechanical things like linear bearings. There's a little bit of stiction involved. Let's support the device using a polyester threads, stretchy polyester threads, which are one of the strongest man-made threads. So we got some, I think they're 4 millimeter polyester threads, and supported the device in a plastic polycarbonate tube. So there was guaranteed no stiction. It would oscillate back and forth freely. We tried many different versions of this. In the top left corner here, you can see the little Tron tank that I was testing. You can see the very first polycarbonate tube that I was working with. And we tried a lot of different configurations of mounting this in the spider web kind of configuration. And found out that going off the ears at the center of mass of the device was one of the best ways to do it. Also, we were doing some testing. And I took the device and set it on the carbon fiber table. And I was doing some frequency sweeps of it, getting the characteristics of the device. And I said, well, I might just well power up the device and see what happens. So I powered up the device, and the device shot off the table. And I'm sure everybody can see that. And I'm sure everybody goes, hey, wait a minute. Something is kind of strange here. What we figured out, this is literally slip stick acceleration. This is what can fool you. Because eventually what we ended up doing, when I got the tracker software a year later or so and started running it, is that when I applied air to this table and accelerated the device went one direction, monitoring the table, the tracker software said that the table goes in the other direction. So this is not real acceleration. It's a false flag. The device was also tested and fully sealed to see how much the device would move. We got characteristics of that. If anyone interested, here's the crystal string, and it says it's strong and stretchy, 100% polyester. This stuff is really strong. I'm really amazed at how strong this stuff is. We tested it, mounting it even vertically. Got some good results. But this is where this is the wart that we have to show. This is the tube supported by the spiderweb structure. And as you turn it on, you can see the screen in the back. As you turn it on, you can see a little bit of an air pump action here. That negated everything. It didn't say that there was not a Mach effect. It just said that it was contaminated by the device pumping air. So we all went back to the drawing table. Woodward and team went back to redoing their vacuum chamber. And I said, well, if I take and enclose the tube and make it so that no air can get in and out, and I put acoustic dampeners on the end, foam board up, and make plugs for the end. If the device does make air, Newton says that the center of mass will stay the same. It will not go anywhere. And that's the next best thing for doing a vacuum chamber. So I did a hanging pendula and got some results. And the results were okay. I did see thrust, I did see movement of the device. But the problem with the hanging pendula is that it has axis of X, Y, Z, and even T. It rotates, it goes up and down, and it goes back and forth. You have to deal with all those components, especially when you got a device in here that wants to wiggle around quite a bit. And especially with a device that may be showing Mach effects. You don't want that to be contaminated. So I ran several hundred tests on this, got some good baseline data, and said, I am going to change the game here. I am going to build a vertical counterbalance torsion arm pendulum. I am going to decrease the mass because I will build the thing using carbon fiber composites, using the C-flex bearings, which They're actually wonderful. They have no stiction. And so I did a carbon fiber arm, vertical arm. The device that you see down here in the bottom is the device is supported in with a spiderweb structure with the foam dampened pads in the back. Found out I really didn't need the extra acoustic dampening. The foam pads work just fine for stopping any air from getting outside and pushing the device. So I took the device, it sits up on top, counterbalance on the bottom. This is a magnet that you can see down here at the very bottom. And there's an aluminum plate. So this is a dampener system. Now you can do a dampener system if you're looking to do this. You can do a dampener system using oil if you wanted to. It gets to be a little messy, but it'll do a nice dampening. You use oil and a paddle in a little container and it will dampen, but a lot of people prefer the magnet. Also along on this bottom pad goes a set of brass weights to offset the mass sitting on the top. So I set this thing up. This is a vertical counterbalance torsion arm. And there's some very good papers online about this, on even oh geez, I'll think of his name in a minute. The group out of Germany, they even did a vertical torsion arm, but I always thought that was kind of complicated, and I thought it was a lot of mass trying to move around. So that's one of the reasons I went with the carbon fiber. It kept the mass very minimal, so it had a very nice response time. And I could vary the mass, the counterbalance mass at the bottom of it, where I wanted it, and didn't have to worry so much about the mass of the torsion arm itself. So I set this all up and ran it, and lo and behold, I get results. This is about a 10-second run. This is a picoscope data that was gathered from a Philtech 18L sensor, about a 1/4 micron accuracy, at the bottom of the torsion arm. And this is a constant frequency. It's not a frequency sweep. So as I hit it with the frequency, the device picks up, accelerates the entire assembly, and you can see it down here in the bottom left corner. You can see where the picoscope data is showing it off. I have some other images I'll show you a little bit later on and show you how this works. Or I'll show you so you can actually see it. But this was the first time I felt real comfortable about saying this, that this actually works. So going back and data mining a little bit, after I did this, I ran the tracker software on the actual torsion balance to say exactly what is happening here. The red dot was a little black dot I picked up off the brass reaction mass. The aqua colored dot is the spiderweb tube that's attached to the top of the, excuse me, the top of the torsion arm. This top display here is the mass A, which is the actual device. So what happens now is I turn around and the device is just coasting along here. I mean, the torsion arm is just oscillating along. It always has a little bit of an oscillation. I turn the power on, off it goes. Here comes the torsion arm following right behind it. I follow it. At no point do I see action, reaction. No point do I see Newton's third law come into effect, the conservation of mass. The device follows, or the device increases its energy into the system by increasing the swing. The device, the torsion arm, vertical torsion arm, is following right exactly with it until after about 30 seconds, I turn the power off and everything starts going back, decaying back down. I'm like, oh, that's kind of nice. So I'm going to do some other tests on this. So I did. What we're seeing here is picoscope data. I have 3 picoscopes that allow me to collect data. On one, I collect, the green here is the current, the red is the voltage. Over on the bottom left here is the FFT display data, and it shows me the harmonics, and the harmonics that are extremely necessary to be able to get a thrust component out of this device. This is a voltage, or excuse me, this is a frequency sweep. The green display here is current. And it's really interesting as you can see how the current varies. And as the current varies, obviously, the power consumption varies a little bit of the device. And it can tell, it says when it's in resonance, out of resonance. So I did the sweep, and it's like, I think I did this from 39.2 to 42.2 kilohertz at about 299 volts. The pico data is at the bottom of the vertical torsion arm, and you can see how it has a nice dampening to it. And it's dampening out, and I hit it with the 299 volts sinusoidal signal. It creeps along here until it hits resonance. Bam. Now I have a deflection of the torsion arm. Now the deflection of that torsion arm holds for as long as that sweep stays within the device's resonance and a high Q. When it runs out of that resonance, the device drops on back and goes back to its normal mode. I went, oh, now that I have the frequency that this device operates at, I can measure that using the picoscope data. I can do a solid frequency without doing a frequency sweep. So this is the picoscope data off the 1/4 micron picoscope data that is at the bottom of the vertical torsion arm. I turn the power on, bam, I get a deflection. It holds. Turn it off, back she goes. Turn it on, holds. Off she goes, off. These are approximately about 10-second runs of sustained deflection. Second page here. I'm like, okay, I'm going to do some testing, but I'm going to do it in shorter pulses, varied pulses. Green here is the current. Everything's the same here. This is FFT display data. This is the voltage and current. Little short pulse, you see a little deflection there in it. The cycle's back down. A little longer pulse, a little more of a deflection. I'll do a little bit longer pulse. You can see more of it, holding it and holding it in situations. This is about 80 micronewtons for a sustained period of time, pushing the torsion arm along. The reason that the signal is decaying here is because I was using a single frequency to drive this. And that as the device heats up, it shifts its center frequency away from my driving frequency, and it decreases the thrust. On this particular one over on the right side, I turned the device 180 around and did the same thing. I did varying sweeps of pulses, and as you can see, I have sustained, this is about 10 seconds here, sustained deflection and sustained thrust, and down it goes. I like the vertical counterbalance torsion arm. It gave me some really, really good data, but I don't like things that wiggle around too much. So I like the frictionless air bearings. So I said, okay, let's do the frictionless air bearings again, but I cannot have that 7 kilograms of mass trying to be pushed around with, 80 micronewtons or more, maybe more. So I will downsize it. I will shrink this thing up and go away from that big, large carbon fiber plate and go to a air slide and just 2 air bearings. And as you can see, this is about as frictionless as you can get. Regular bearings will never quite do this. This is a Lufkin leveler. Divisions are about 0.0005, which is about 12.5 microns per division. So it allows me to level that table. The problem is if you're using air slide and you're using anything with mass on the air slide, that table better be very, very level, or it'll go one direction or the other. And you will not get a balanced response out of it. So this makes it very nice to turn around and level the table. So I did. So I took my spiderweb tube and closed on the first set, and I did some runs on this. But I wanted a vacuum chamber, and I couldn't figure out how to get a vacuum chamber. So this week, I don't think I could get it in my house. So I went, it'd be nice to put a vacuum chamber on an air bearing, wouldn't it? I mean, but that'd be like trying to shove, 100 kilograms or 200 kilograms up back and forth with this big stainless steel aluminum can. I got to do something better. So I did. I said, you know what? Really, the only thing that's really important is to put the device into vacuum. Everything else is just huge. So currently, I'm in the middle of a build. I used a 1/4 inch walled polycarbonate, 3.5 or 3.25 inch long polycarbonate tube with end caps, polycarbonate end caps. I have a vacuum valve that I built so I can bring the vacuum line over to the vacuum valve, evacuate all the air out of it, disconnect the vacuum tube. The device will maintain the vacuum, and it has maintained the vacuum in preliminary tests. I have it, which is really good. The thing I could not use on this particular device was I could not use the polyester threads. Polyester threads and vacuum just don't quite go together well. They like to outgas, and it'll change their characteristics. So I said, how can we support this device without killing it off as far as it's vibrating back and forth? And I found a set of tweeter coils that'll fit right in this tube, this polycarbonate tube. And the dome on the tweeters is made out of titanium, which I cut a hole in the center of this and mounted the device in the center of mass on this titanium dome that I'd cut out. And now I have all the structures that allow the tweeter speaker to move back and forth very freely. So this is in the works right now. But I did do some testing using the air bearing. I wish I had more pictures, but I haven't taken a lot of pictures on this. This is a frequency sweep, just like I did in a couple slides before this. So I did a frequency sweep from 34 to 36 kilohertz at about 300 volts. And I monitored the movement of the sled using the Philtech 89L sensor data. It was about 1/4 micron accuracy. Fine, 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 until it hit resonance, and then off the track accelerates. The entire track is moving, sitting on a set of those virtually frictionless air bearings. Same display down here, bottom left is FFT. This is current. This is current actually at the end of the sweep, so there's nothing there. I went, well, this is really pretty good. I'm going to use the tracker software and see exactly what is happening with the device in the sealed tube, the sealed spiderwood tube. And I did. I was able to go through the device, look through the wall of the device, pick a screw off the end of the device and say, I'm going to monitor the movement of this device back and forth. Lo and behold, here's the device, nothing until I hit resonance. So bam, now I have a nice accelerated curve and it sustains itself and it goes off the screen. This is where I'm at on the testing of the Woodward device. Thank you.
So Michelle, are you all set?
I am, yeah,
Okay.
I have no idea how long I went.
So what I'm going to do is I'm going to remove the spotlight and let me see. So you guys are at, you guys are pushing 2 hours. Allow participants to unmute themselves. So let's do this before we go any further. And hopefully I've got everybody unspotlighted here. I'm going to go to gallery mode. Everyone, please give an enormous applause to Mr. James Woodward, Dr. James Woodward, and Michelle Broyles.
Good job.
Thank you both so much. Again, it is a tremendous honor. You know, as I mentioned before the conference, this conference was inspired by Estes Park. Mark Sokol and some of his colleagues went to Estes Park online during the pandemic, and they realized that the potential for using Zoom to put on an open scientific conference was so enormous. So that's really what kickstarted the whole thing. And you know, we've been able to leverage things, but we've always tried to kind of keep that, again, the spirit of what you guys created with Estes Park there at the center of this. You know, it's an open scientific online collaborative environment. So thank you. It's a tremendous honor to have you both present today.
I really just want to say thank you for having us on. It's sometimes when you have like an Estes Park meeting, it can get to be so intimidating with such wonderful minds, wonderful ideas, and wonderful thoughts. It's really nice to be able to have a concentrated presentation, to be able to get your points across. And I hope I did, and I hope Jim did too. And one of the things I know that we wanted to do, both Jim and I and the entire group, is to convey what he has done is like 20 years worth of work on the torsion arm pendulum and stuff. Well, maybe not 20, maybe what, 10? It's a pretty detailed setup that he has. But what I presented is something that a regular person can do. Somebody that has a little lab or wants to set up a little lab, there's nothing that is complicated that was built that I had done that they cannot build for a couple $100. And they can get results. And that was the important thing I think I wanted to convey in my presentation, that there's nothing really complicated there.
Yeah. Well, you guys, I mean, you have such a tremendous legacy of work, you know. When I first got into this, I mean, Jim's work, I was reading about his stuff back in the 90s. So and that it had been around then. It's just this tremendous ongoing legacy, and I've gotten a lot of the announcement emails and stuff too, and I get Jim's update emails, and I see this continued progress and continued testing. And it's just, over time, it continues to build and grow. And I think that's kind of the best kind of science, it's just this organic evolution over time. So again, thank you both for presenting today. And thank you to Paul March as well. Paul wasn't able to be with us. Hopefully he'll be able to present in the future, but I'm glad that we were able to capture his presentation. Thank you guys for showcasing his work as well. So let me do this. Let me put this on speaker mode. And again, hopefully I've got the spotlight, unpaused there. Let's go to Q&A session. So again, it is Option Y on Mac and Alt Y on Windows. I believe I didn't mix those up. If you guys want to raise your hand to ask questions to, and there's Mark. Go for it, sir. Mark. Okay. And Mark, it looks like your mic is live, but I am not getting any audio, sir. Yeah, and again, to raise your hand in Zoom, it's Option Y on Mac or Alt Y on Windows. And I'm scrolling through chat here too. So with chat, it doesn't look like we have any questions. It looks like we have lots of comments. Yeah, it looks like Mark's. Oh, okay. Mark is typing into chat. Okay, well, let me go. So Mark, while you're working on that, let me go to Jared. And we'll come back to Mark's question. Jared, go for it, sir.
Excellent presentation. Really, really appreciated all that you guys, all the work you've done on this thing. I had two questions about it. One, it seems like you're dealing with a lot of non-linearities in these things. There's a lot of moving parts that are moving against each other, moving at different phases, all that kind of stuff. I was wondering about the frequency sweeps that you guys were using for it. If they were always linear sweeps, or if you ever did non-linear sweepings, or arbitrary waveforms, or that kind of thing.
Okay, I guess I'm the person to ask that question of why use frequency sweeps as opposed to running a constant frequency. The problem with running a constant frequency, there are two problems. One is getting constant frequency relatively close to a very high Q signal turns out to be tricky. The other is that heating, which takes place when you're near resonance, it heats up fairly smartly, causes the resonance to move. So if you want to be assured of getting the, how should I put it? You want to be assured of getting at least a brief pulse of the full Q of the device, sweeping on it ensures you that you've got a really good chance of hitting it. Okay, you won't hit it for very long, but you will hit it. That's the reason what you were looking at in run 7 on August 12th was with the sweep rate low, slowed down from what I had been using before that on that day. Michelle is a, I'll let Michelle speak for herself. She likes running a constant frequency.
Yes.
Yes. With her system, she's managed to get reasonable results running at constant frequency. With our system, we have, as I say, the problem of signal getting buried in noise. If you don't, unless you are dead on the signal itself, and the signal is large. And I really don't know what's in the works out of all of this is going to be a paper that will hopefully be published in a credible journal and so on. And to make sure that the results are presented both ways, both constant frequency and frequency sweeps. My own view is that looking at it from the point of view of commercialization is that a commercialized device is likely to run with short pulses of swept frequencies to ensure that you get the full resonance effect, and then you just go back and sweep over it over again and again and again. So you're running at constant frequencies as opposed to constant frequency. I'll let Michelle take a swing at this one. Go ahead, Michelle.
Well, there are two ways to run this. If you do a frequency sweep and you do it pretty fast, you could get the device to accelerate quite a bit. And you may get a little bit of extra thrust out of the device itself. But the data that you pull off of that is very hard to say, okay, this is what we have thrust. And when we did that one picoscope data that you done on run number 7 from August 12th, when you showed that to a lot of people, it looks like just a bunch of squiggly lines up and down, even though you may have a nice thrust pulse in maybe the millinewton range or half a millinewton. My goal here is to say, okay, I'm going to put data together and do a constant frequency pulse and do it for like 10 seconds or maybe sometimes longer, as long as I don't overheat the device, as long as I take the device and keep it within its temperature envelope and get a constant, steady thrust pulse. That, I think, more than anything else, is telling a lot of people, yes, here's this Mach effect. That's why I went with the air-bearing slide. Probably when I end up getting the full air-bearing slide done, I will do a series of short sweeps and pulses to see if I can get a higher acceleration out of that, and I also will try a steady state. But I've also had to turn around and I've set the frequency just that below the resonant frequency, turn the device on and let the device, as its resonant frequency decreases in frequency, drop down into my driving signal and see if I can't get a little bit of extra oomph out of it, a little bit extra runtime out of it. But that's not something you want to use for shoving in a CubeSat or anything. So, but that's the reasons I have done the steady state, is turn around and get nice clean data that that can be presented, that can be show people that yes, there is this Mach effect. And we have changed how we have done our signal generation. We have went from, a sinusoidal, we have tried trapezoidal, which is sawtooth, and so on and so forth. There's a lot of different ways that you can excite this device to make sure that you get better harmonics out of it. As a matter of fact, a member of our team, David Jenkins, is designing a driver for this. And it's been about, what, a year and a half now, 2 years, Jim, that he has done this absolutely wonderful job. And I expect that when we're all done with that won't have to really worry about whether you're doing a sweep frequency or whatever, that we'll be able to drive this device keep it within its temperature range and get continuous thrust out of it, or pulse thrust for extended periods of time. That's about what I have to say.
Awesome. Okay, well, and let me jump in really quickly. We've got about 8 minutes until the top of the hour, and then Franc Milburn is coming on then. So let me try and get these 2 more questions in. And again, you guys have both done a marathon today in terms of presentations. So let me see. Mark Fiorentino was asking, and he typed it in. He at first he'd asked, when you achieve resonance, is the waveform balanced or symmetrical? And he's also asking if the resonance equals propulsion. It seems that the oscillating waveform would have to be non-symmetrical. So those were Mark's questions. And again, Mark, I'm sorry that you're having mic issues today, but
Is it? Yeah. I'm
oh,
sorry.
now it's working.
That's working.
Now it's
Yeah,
working. Oh,
I plugged it in and unplugged it and plugged it in again.
yeah. Well, yeah. Let me put that out there to them. And
Okay.
again, we'll try and go until the top of the hour when Frank comes on. So okay.
Okay, waveforms. Up until fairly recently, we've been using sinusoidal driving waveforms. The nonlinearity in our system actually alters the waveform by adding higher harmonics. You may recall I made a point of pointing to the transformer in Paul's block diagram of the circuit. It turns out that that transformer is a critical element in the operation of these devices. It doesn't make any difference whether they're talking about SM111 or other materials, at least one of which works after a fashion. Okay, you get the second harmonic, third, fourth harmonics, and they can in fact be quite pronounced. The waveform as a consequence is not symmetrical, as you noted. Our data collection technique is to display an oscilloscope display with the picoscope the waveforms for the voltage, the current, the strain gauge or accelerometer, as you choose to call it, so on, and then the computed instantaneous power, which is the product of the current and the voltage, gets displayed. The movie that I wanted to show you, and indeed, actually come to think of it, Michelle made a very low resolution version of that. I wonder, maybe, Tim, can I share the screen on this?
Yes, if you'd like to give it a try, go for it.
Yeah, I think I've got Michelle's movie. Let's see, how do I do that?
Yeah, and it doesn't look like Frank has joined quite yet, so we may actually have a little bit of extra time. So
Yeah, how?
it's so Jim, it's the green share screen button. It should be at the bottom center of your screen.
There we are down here. Okay.
Yes, sir.
Share. Okay. You cannot move video. Well,
Let me say
Yeah.
this, a very
It
high
is.
level.
all right, let me see if I can find that. Some glasses. Okay.
There's so much more that has happened in this
Oh, and
there's work. Always is, you know. We've done video processing with MIT software that was developed by MIT. It's motion enhancement software to be able to discern movements that you cannot see with your eye, to expand them out like 50-fold.
And you know,
So-
I'm not sure if you guys might be interested, and this isn't the best time to ask, but it might be interesting to have you both back to just walk us through all of these videos. You've had so many test videos.
You're watching Run 7, the spectacular one. The waveforms are in the center bottom. Okay. Red is the accelerometer, blue voltage, and green current. And they are obviously non-symmetrical. Okay, it's a consequence of having the circuit be intentionally nonlinear. Okay, actually, it was accidentally nonlinear, the way in which this became obvious, and so on. You can, all right, now this is going to. Okay, it's going to stop. Okay, let me explain the screen. The upper left rather, is the strip chart recording of thrust, which is red, the voltage, which is blue, the strain gauge or accelerometer, which is brown or gold or whatever you want to call it, and the temperature, which is green. Okay, and then you notice in this display is that there is a glitch in the ground trace where the thing goes negative. There's a corresponding change in the blue trace too, and the blue trace picks up the oscillations before and after the negative going part of the signal. The center bottom is the waveforms, as I've explained, well, as I've mentioned. A blue is voltage, red is strain gauge, green is current, and in the lower left, you have an FFT of the current trace, which shows the nonlinearities most spectacularly in the system. If your screen is not set up, so I think, Tim, you got the people's images up side by side in a block of 6. Is there any way you can put 3 of them down below and get a little more to show? And I'll run a video again real quickly.
Oh, it may be displaying differently on yours, Jim. On mine, it's got you on the side in very small, and then it has, actually, it's got your video in the Windows Media Player.
Yeah.
If you'd like to run it again, we'll do that. We're just about 2 p.m., so we may not be able to get to all of our questions, and I should apologize for that. If you want to give it one more run.
Here we go. This is with the sawtooth waveform. As you can see from the blue trace, it's pretty much sawtooth, but you can also see the higher harmonics on it too. And on the right, you can see the thing actually moving around. Let me real quickly make one comment on this. We have not yet done the sort of check test to make sure that there's not something fishy with this, mainly because we've had this system. This system has been in operation here off briefly because of the pandemic, but on most of the time since 2010, 2011, thereabouts, when the present thrust balance was designed and built. Okay. So we have a pretty good idea of, for example, one way of testing this is to replace the device itself with a capacitor or set of capacitors with the same capacitance and run them in this. And when you do that, what you find is you do not get the thrust effect like this, any thrust effect of this sort. Another way of doing this, which we discovered accidentally, is to remove the transformer from the circuit. When you do that, all of those really pretty higher harmonics that you just saw in the movie pretty much go away. And of course, you don't see any thrust, even when you're running at higher power than you need to run at to get this to work. So I will unshare the screen. if someone wants to see the movie one more time.
Okay. Well, and so, yeah, we're just past the top of the hour and it looks like Frank is there. So let me unshare the screen for you. Jim, unfortunately, we're not gonna be able to get to the other questions, but let me do this. I want to put this back on gallery view, and everyone, please give an enormous applause to Dr. Jim Woodward and Michelle.
Thank you, thank you, thank you.
Thank you both.
Thank you for having us.
Yeah, and thank you both.
I'm
for
sorry
joining us.
Paul March couldn't make it. I know he was looking forward to it. We all miss him and wish him well.
Well, and
Yeah.
we'd love to have you back. Maybe we could dig more into, if you're open to it, and we can talk about that after the event. But if you're open to it, maybe we can run through more of the videos and just anecdotal stuff, and come back to the questions that we had from this one. But again, thank you so much for your time. It has been a tremendous honor to have you present. And really, you guys are, what you did with Estes Park, that inspired this conference. So, you know, your spirit has been with us since the very beginning.
Thank you, thank you.
Thank you very much. Thank everybody for joining and listening.
Okay. Okay, so let's do this. I want to put this back on speaker, and